Hello! Welcome to our very first lecture on stats. So that sounds super dull. I apologize. I'm gonna do my best to make these as interesting as possible. Basically what you're gonna need is the note packet that is also up on Google Classroom. If you want to print that out, that might be cool because then you can write in things along the way. Or you can just split your screen and have this going on in the background, and on the other part of your screen have the notes from Google Docs so that you can type in as we go. This is pretty crucial, whatever system you set up to use, because this is what you will use when you do your exams and your homeworks. Like I said, there's no formal book. There are only these killer note packets and these videos that go with it. So I'm going to get this alert every so often. I can't figure out how to turn it off. Honestly, I haven't really tried to figure out how to turn it off. I just, exit out and ignore it. So I apologize, those are going to come up. Alright, so where we start out with is research questions. The thing about statistics is that it is intimidating, particularly to the uninitiated, and I get that. I try to be sympathetic to this. And there's a lot of attention in research on statistics, but statistics just fits in one little part of the whole process. And really, the primary motivator and driver behind research is your question. The question sets the stage for the whole thing. And it's a really integral part of human nature is to ask questions. We ask questions all the time. The research process is that part, that systematic way that we ask our questions and then figure out a process by which we answer them. So just real quick, I'm going to go over this. You probably have heard this since you were in elementary school. So the first step of the research project is just to ask a question. Not all questions are created equal, and we're going to talk more about that, but you have to start with a question. And then from the question, you delineate even more specifically into a hypothesis. For this class, we're going to talk about hypotheses in the terms of statistical hypotheses. So in a few weeks, we'll start hypothesis testing, and that's when we're using numbers to actually try to test our question to see what kind of evidence we come up with to either support our question or, you go back to the drawing board. So after you formulate your hypothesis, then you have to go out and you have to collect the data in some form. After you get the data, then you analyze the data. So this whole class, everything that we learn, really is only applicable for part D of the entire process. So while statistics is really interesting and powerful, and I feel super compelling, it is really just one small slice of a much larger thing. After you analyze your data, then hopefully you've got some answers. You can go back and evaluate the hypothesis, see whether or not you've got support for, your original question, or whether or not you need to go back to the drawing board. So okay, I guess I should also admit, I love Pusheen, and Pusheen is my stats mascot. So you're going to see a lot of Pusheen in these PowerPoint slides. So Pusheen here wonders, I'm not fat, I'm poofy. That's something that we could go out and we could evaluate, whether or not Pusheen is poofy or fat. We'd have to define what we mean by both of these terms, the poofy or the fat, but we could go out and we could observe it. We could collect data on it. We could analyze that data, and we could come up with evidence that supports whether or not Pusheen is indeed poofy. So a good research question. Good research questions have three components. They're testable, meaning that you can go out and collect the information, that it's possible to collect that information and then turn that information into some kind of data. Good research questions are empirical, meaning that they can be observed and measured. It is possible. There's already either things created to do the measurements, like numeric scales, weights, tests, measures, or, we just haven't come up with it yet, but it is possible. The key thing here is an empirical information is something that you can actually observe in some way. Sometimes it's just an artifact of what happens. Some things we're not able yet to observe what the actual process is. We just see what happens after that process has happened. The third thing is that a good research question has a theoretical foundation. So this is the whole explanation for why two things are related. And at first, sometimes we think, you get a hunch, you think two things are related because of your own lived experience. But for research, you really want to move beyond your own individual or anecdotal experience to more of what others have experienced. Like, you're trying to bring many things together. And so this is really where literature reviews come in handy, because in the literature that is peer-reviewed scholarly research that's built upon larger theories. Doesn't mean you can't use research to develop theories or change theory, but it's a theoretical foundation is a good place to start. So a good testable research question has the following components. You need a dependent variable. These are the effects. It is the thing that you're interested in explaining. And typically for statistical research, you only pick one thing at a time. The more dependent variables you have, the added complexity you have in a statistical model. Independent variables are the causes. They are what you think are impacting the effect. They exist, they have a thing, and then something happens in your dependent variable. Now for independent variables, you can choose more than one, and it's highly encouraged to have more than one, because the world is really complex. We know that for anything that we're interested in, whether it be poverty or voting, there's a lot of things that influence those conditions. So we want to try to model as many things that we think influence as possible. Now for this class, we're going to start out really simple. We're going to start out with like just one variable at a time. How do we describe it and explain it and understand it? And then we add in another variable, and we'll look at like, how do two things interact with each other? At the very end of this class is where we get into like, okay, let's build a big model and have multiple independent variables. Your choice of independent variables should also be driven by theory. You should be looking at not only what you think matters, but what other people have said matters as well. And the last thing that every good testable research question has is a unit of analysis. The unit of analysis is like the subject of a sentence. It is the who or what that you are measuring. And this is kind of tricky, kind of like hard sometimes for people to wrap their minds around, because if you look at a data set, there is always a unit of analysis, and it is typically who are the rows, right? Like, who are you measuring? But the unit of analysis can change, right? Like, it's not the same from one data set to another data set. And you can have multiple units of analysis in a data set, which make things even more complex. Examples: states, cities, peoples, school districts. These are all things that could be units of analysis. So when we get to the point where we are looking at data and we're analyzing data, one of the first things I'll always point out when we open up a data set is, what is the unit of analysis? A good research question has these three components. It's falsifiable, meaning it's not written as if we already know that it's true. One of the biggest hang-ups that students have when they're first writing research questions is that they write their research question as a statement. Like, voting is a public good. Okay, that's written as if it's not able to falsify, right? Like, it's written as if it is already true. A good research question has explicit comparison, meaning there's a unit of analysis. So we're hoping to have instances where we observe something is happening in some areas, and maybe there's less or more of it in other areas, so that we have comparison. A good research question also states a direction, meaning that in the question it says that there's more or less of it, it's increasing or decreasing, or there's positive or negative impacts on some things but not on others, or more in one area and less in some other areas. In a poor research question, there's typically the insertion of things like values or morals. We say things are good or bad. There's unobservable phenomena, like, is there an afterlife? Is there a hell? Or is there heaven? Is this really the good place or not? Like, these are things that are really interesting, right? Like, it's not like social sciences just rejects those things. Sometimes people have painted it as if it does, but really it doesn't have to. It's just social sciences are really good at answering certain kinds of questions, and they're really not good at answering other kinds of questions. And so in a research question, if you are interested in the afterlife, like, that's legit pretty interesting. But, you know, like, because of ethics, it's really not okay to, like, get people together for a study, kill them, and then bring them back. like medically kill them. I'm not like murder, stabby kind of thing. But like, that's unethical, but it would be probably the cleanest or clearest way to objectively say, like, okay, so when we killed you, did you observe like a tunnel of light? Did you hear music? Did you hear any other voices? Like, it would be really cool to know, but like we shouldn't do those kinds of things. So unobservable phenomenon don't belong in social science research questions. And again, a poor research question is going to be stated as a fact, or if it was always true. Like I said, that's the number one hang-up that I'm going to see in research questions, so that's why I put it on there twice. So here's some examples of bad research questions, and I would encourage you to pause the video after I read these and then see if you can rewrite them so that they fit this model of what a good research question is. And if you don't like either of these, like come up with your own. It's totally cool. I'm not gonna know. But one example of a bad research question is voting good for society? So in one sense, like, okay, great, you stated it as a question. There's something that you're interested in. But there's some problems with this. There's some squishiness in this language that needs to be tightened up. A second bad research question is raising a family in the country better than in the city? Okay, this one's a little bit like a trickier one because it seems okay at face value, but there's some issues with this one. So I would encourage you to pause the video, write down some revisions for this one, and see if you can clean them up. They need to have a clear direction, they need to have a unit of analysis and a clear dependent and independent variable, and they also need to be stripped of values or morals, and they need to be written in a way where we can actually observe things and determine whether or not we could have evidence that supports it or doesn't support it. A good research question, there always needs to be the possibility that there's no evidence in support of it. So after you've done that, come back and let's pick it up with causality. So, quick story. Over the summer, in two completely different platforms, one was Twitter and one was my Instagram, I saw these two images and could not help myself. I was like, ooh, that's interesting. So the first one on the left is looking at Google Trends for the search of God by country or metro area. And you can see this pattern where there's this lighter greeny, yellowy colors all sort of in the south and then wrapping up around the corner of Missouri into Oklahoma and Kansas. And this is showing an increase in Google Trends for the search of God. We don't know what they're searching. We don't know that these searches are indicative of, I don't know, spiritual quandary or a search for God or a meaning for life. But if you feel your brain jumping to those conclusions, you're thinking like a scientist. You are trying to draw connections and patterns in the data. This is one of the things that I love about good data visualization, is that it encourages that curiosity, that engagement with the data. And then next to that, we've got this other picture. Now this is a map showing the political vote for the Electoral College, and it's based off of polling. This is later in the summer, like I'm thinking early July, maybe late June, I'm not sure, to be honest. Likely this has changed because the election, it's not till November. We don't know what these states are actually going to look like because it hasn't happened yet. So this is just sort of one snapshot in time. But the thing that was interesting to me is that the shading, the darker, lighter of the reds and blues indicate whether or not, according to these people, that state is considered safe for the Democratic candidate or safe for the Republican candidate. So the lighter shades of blue and red, indicate that there's some political leaning in this way. Like they're not sure. And when you look at these two maps side by side, you might be inclined to be like, well, I don't know, Kentucky. If you had yourself, in Tennessee, if you had yourself sorted on the God question, maybe you'd know where you're at politically speaking. That jumping to the conclusions, that trying to find a pattern and find meaning in these things, that is reaching towards causality, and it is not okay when it comes to social science research. You shouldn't do these things without some sort of metric or process to see, is there actually a relationship here? And so the way that we determine the nature of the relationship is this process of causality. So causality is establishing that there is a relationship between two variables. And it is causality itself, we could say like, oh, there is a causal relationship between these two things, like a causal relationship between your view on God and your politics, which I don't know. I don't think so. Maybe. I don't know. Causality is the highest level of evidence or of relationship. Like, causality means if this first thing happens, you always, 100% of the time, get this result. And so it's really hard to do in social sciences. Why? Because in social sciences, we study people, and people be cray. I mean, have you seen people? Like, there's always some confounding feature. There's always some evidence or something that breaks the rule. So we strive towards causality in social sciences, but that's not the high bar you're reaching for in terms of like, if I don't reach this, I'm never going to get published, or if I don't reach this, nobody's going to take me seriously. There's many steps in between. So while we strive for causality, our real process and search for what's happening is more like this image down here, which I mean, this gave me a good giggle. It was from my Instagram feed, a chronology of 2020, where time seems to be moving in this like straight linear way, and then COVID happened, and it's like, oh my goodness, time just has this sort of very weird feeling. I cannot believe, like, in some ways March feels like an eon ago. And yet when I think back to June, I was like, wow, it was just June like 2 seconds ago. The summer's over. So in order to build this case that there is this relationship between two things, which is part of what we use statistics to do, this helps us build an understanding and an evidence base, we have to meet a certain number of conditions. There's 3 of them. The first one is time order. So in order to establish that there is a relationship between two things, your cause or your independent variable has to come before the effect, which is your dependent variable. So in this case, my little picture here, my sense of time has been impacted by COVID. So what I'm trying to understand is my changing sense of time. That's the effect. And what I think is influencing my changing sense of time is a global pandemic. That's the independent variable. Covariation is whether or not you get changes in your independent variable, do you also get changes in your dependent variable? So when one thing changes over here, do you see some change in the thing that you're really interested in trying to understand or explain? We're going to talk a lot more about covariation when we get to correlation and regression later on in the semester. We'll get to do some fun covariation calculations. The third thing is you've got to try to control for alternate explanations. In fancy stats term, this is called spuriousness. Controlling for alternate explanations is really important because the world is complex, and if you build too simplistic of a rationale or a model for why two things are related to each other, you're going to miss something. You're going to miss something big, potentially. Something that could actually, if you had accounted for it, explain away what you think is happening. So the classic example here for spuriousness and not controlling for alternate explanations is ice cream sales and murder. Murder has this sort of cyclical pattern, the murder rates do. And they go up in summer months and they go down in winter months. It's kind of interesting, but that aside, if you were only looking at ice cream sales, which also have a cyclical pattern, you might, well, actually, if you just put the data together and run the analysis, it shows like, yeah, there's a really strong relationship between ice cream sales and murder rates because they follow the same cyclical pattern. Ice cream doesn't kill people. Well, I mean, I guess it's plausible. You could create a situation where ice cream could kill somebody. But the sale of ice cream, the consumption of ice cream, does not typically lead people to like go out and, become homicidal maniacs. It's an artifact of something else, the weather. So if you were only looking at two things, ice cream sales and murder rates, you would be, led down a path to draw a really not accurate conclusion about the impacts of eating ice cream. So something else I'd like for you to do is, here's another pause point. You need more practice. Like, you cannot practice enough writing good research questions. And in your first assignment and in the first exam, you're going to have to do this. In fact, in the first exam, you'll have to deconstruct 2 research questions, and for your first assignment, you have to write research questions. So something you should do here would be to look at these 2 statements and see if you can identify what is the dependent variable and the independent variable, and if you can identify the unit of analysis. Who is the subject of the sentence? What are we trying to explain? And what do we think is influencing that? Down at the bottom, I've got this template, and it's pretty rigid, I'll admit, but sometimes when you're writing these, if you've not done it very often, it's good to use a template, because then you know you're getting everything in the way that you should. Like, you know that you're writing them correctly. And once you get used to it, then you can get more artistic with your sentence structure. But if you follow this template, you'll at least know that you're getting all the components in that you need. You're going to get all your points, is one way to think about it. So something I encourage you to do would be to either use some of the bad hypotheses that you rewrote, or rewrite a hypothesis, or when you look at the first homework assignment, see if you can make it work using this template, and then run it by me during lab hours, or run it by Vidalia during lab hours, and see how you're doing. Okay, next big thing in your introduction is we got to talk about measurement theory. Now, measurement theory is pretty tense. Like, this is where you're gonna see people losing their shit. Oh crap. Okay, so sometimes I might curse because I'm alone in my closet just talking to a computer screen, so you're gonna have to let some things slide. But in social sciences, where you see people get really like red in the face, mad about stuff, is when you start going after their measurement and talking about, well, why did you quantify this concept using this number, or why did you use it this way instead of that way? Like, this is where people get really nitpicky. And like, I mean, Pushin's got it straight here. Haters gonna hate. One of the like, when you do literature reviews for like a senior seminar, sometimes you'll find these things where these back and forth arguments between scholars about measurement and the validity of a measurement. This is the juicy tea in social sciences. I know you're probably sitting there thinking like, Laura Weedlager, you're a nut. I am a nut, but I am not lying to you. Like, this is the good stuff. So measurement theory is this idea, this argument that we can measure things. We can measure lots and lots of things. Like, we're going way beyond just like height and weight and eye color kinds of measurements. We can measure depression. We can measure anxiety, poverty. We can measure cultural phenomenons. We can measure, you think of it, we can measure it. It's this idea that like, not only can we measure and describe it, but we can attach a number to it. We can tell you how much or how little of it there is. And the way that we do that is that there are ways to empirically observe. Like, we can see it with our eyes. We can count how many times it happens. We can look at the specific behaviors and use that as an attempt to measure some sort of phenomenon. And we use numbers as a proxy. So when we open up a data set in Excel, you're going to see just like wall-to-wall numbers. But something I want you to keep in the back of your mind is that those numbers are going to be used as a way to conceptualize something else. So when we look at the percent of the population in a state with a bachelor's degree, we're going to use those numbers as a way to say, well, this is why some states are wealthier than others, because they got smarter people in their states. That's measurement theory. That idea that you can take a number and then use that number to approximate some larger, broader concept. This is where people get really uncomfortable. Like, in faculty meetings, there are times when we're trying to measure something like student persistence or the likelihood of the student's going to be successful or not. And the social scientists in the room were like, oh yeah, we can do this, we'll use that. And then you get the natural scientists in the room, particularly the mathematicians, and they're just so uncomfortable. Because mathematicians don't really believe in this kind of measurement theory. Like, mathematicians they want some things that are like a little bit more concrete. And even that is like, I need to take that with a grain of salt, because mathematicians do some real wackadoo, crazy, out there kinds of theoretical mathematics that just kind of like make me nauseous to think about. It's just all disciplines have their out there moments, but when like social sciences out there moments are not the same things as the natural scientists or the humanities. It's just something to keep in mind. So within measurement theory is this argument, this idea that we can measure things accurately, precisely, and other people can do it too. It's repeatable, and we can do it in a way where we minimize random error and try to eliminate systemic error or systematic error. I'm going to define what these two things are. So random error. This is stuff you got no control over. This is somebody's sick when they take your survey. This is that, punk kid who just wants to mess with you and lies about all their answers. It's gonna happen. It gets in there, and we just assume that over time, the extremes will cancel each other out. Or when we're doing our statistical analysis, we'll have ways to identify these kinds of errors and control for them. In fact, there are specific things in more advanced models that actually put a number to the random error to kind of try to account for. There's always some amount of error. We're not striving to be perfect here. We're striving to be consistent. Systematic error, though, that's the one that's going to make you real sad. Systematic error is something that's going to ruin your work. It is a fatal flaw. It is a bias. It is a poorly worded question that gets you wrong answers. It is confusing wording where people don't know what you're asking and then don't give you answers that reflect what you're trying to measure. Systematic error is something that's going to impact every single participant. And so all of the information you gather is got this bias or this flaw in it. It will drive you to drink when you find it, particularly if you've dedicated years of your life trying to collect information only to find out later that it's not going to be usable. So, when you are out there in the wild looking at data, how do you know a good measure when you see one? So I'm going to explain this using the example of taking the Spanish placement test. Okay, so the Spanish placement test. First question, is it a valid measure? Well, yeah. You have to demonstrate some ability to read and comprehend the Spanish language. You have to speak Spanish a little bit, and Professor Wilson will determine based off of your speaking skills what level Spanish is appropriate for you to take. An accurate measure would be one in which the test is actually measuring what you're trying to measure. So in this case, the Spanish placement test, you're trying to measure how much Spanish somebody knows and understands. And the way that we give out the test, you're consistently, accurately getting a good assessment of how much Spanish someone knows. Precise, are you measuring what you think you're measuring? So an imprecise measure would be if Dr. Wilson wasn't able to give the Spanish placement test, so he's like, hey, weed locker, will you do this for me? And I'm like, sure. And I pick up a German test, and then they're asking you questions about German, and you're like, I don't know any German. And so I'm like, this person doesn't know any Spanish, right? Like, that's an imprecise measure. A precise measure would be something where you are asking good questions and you are engaging during the dialogue part in a way where you're going to get a good, really clear sense of someone's knowledge and ability to speak and understand Spanish. Repeatable is consistency. It doesn't matter that the Spanish placement test is used in Carlinville, used in San Francisco, used in Toronto, used in New York City. It's still measuring people's knowledge of the Spanish language. So random error would be you're really sick when you take the Spanish test, right? Like, your head's all stuffy, you're like hopped up on NyQuil, and you don't hear some of the questions, or your brain's just not fully functioning, And so you miss some things that normally you wouldn't, but like you were sick. That's random error. You didn't mean to be sick, it just happened. Systematic error would be like giving you a language test in a different language than the one that you had studied. So our next topic is classification of data. This is another foundational thing that you need to start getting comfortable with. This is a lot of this intro to stats stuff. It's just the language that we use, because a little bit is you're going to have to learn a lot of new vocab words. So we break down data into 3 big groups. The first one is nominal. So nominal is a really simple classification. There's no really order of the values of the data. It's basically, if it's a nominal data, you don't really get to compare the individual observations to each other, not in any way that's meaningful. Nominal data is used to identify information, particularly to identify units of information. So examples here, in this little box here, I've got the variable name for some variables like the state, the region, and the label, so for state, is the name of the state. So names of states, that's nominal level data because it's just naming the states. Now you might have some values about which states are better than others, but just looking at the data, it's not clear comparability, it's not clear that one is more or less than another, it's just identifying them. Ordinal data is ranked data. This is telling you the ranking of whatever your units are from first to last. Now, hold up. Just because you can sort the data and put it in order from greatest to smallest or smallest to greatest does not make it ordinal data. That makes it sorted data. Ordinal data is the actual numbers of the variable are already in the rank. So it's easy to make them because you can just sort the data and then create a variable that's first, second, third, fourth, and so on. The example here in the variable data set would be the comp rank 01. So this is the rank of computer access by state in 2001. So you're going to have a state that's first, a state that's second, a state that is third in terms of the rank. But you don't know the distance between the rankings. Like the distance between second and third place could be really close. Like they could just be off by like a percentage, or they could be off by like 15%. You don't know. All you know is that one of them is second and one of them is third. Most data is interval or ratio data. Now, I don't ask you to know the difference between interval or ratio. We just lump those together as a third group. Interval ratio data is actually most of what the data is that we use. Anything that is a percent, anything that is a count, anything that is a rate or a ratio, those are all examples of this kind of data. The thing is that these are numbers that run the number line. They can be added and subtracted and divided, and you can do all the mathematical operators to them, and you do so in a way where it's meaningful. The numbers they can be broken down along the number line, and so that you can tell the exact differences between two observations. So the difference has to do with the treatment of 0, if you're interested. In one way to think about it is like in temperature. So if you get a 0 degree, it doesn't mean that there's the absence of temperature outside. It means it's really freaking cold if it's 0 degrees. But you can have a 0 in terms of like, if you think of dollars, and $0 means you're broke. You can have $0. In fact, you can have negative dollars. You can owe money. So that's the difference between interval and ratio. It's that treatment of the value of 0. But again, that's, I don't know. It doesn't come up in this class, so we just lump that together. All I want you to know is that there's 3 big groups. There's nominal, there's ordinal, there's interval ratio data. A few other lingo for data. And these are just other terms that I use all the time, and there are other terms that you'll probably see if you look at textbooks or other supplementary materials online. So discrete variables. If you hear someone use the term discrete, it means that they're talking about data that takes on a specific set of values. So yes, no. Those are discrete. That would be a discrete variable where And sometimes we use numbers too for discrete. Like we might mark yes as a 1 and no as a 0, but we don't use any other numbers. It's either a 0 or a 1. A continuous variable is interval ratio. It means that you have a variable that has values that run the number line. Another term for this is also scale. Sometimes you'll see this as a term. Scale means the same thing. It means that you have a variable with values that runs the number line. And you know, like I was worried it was getting boring, so I put a cute little Pusheen little comic there. I just love that Pusheen. He's so cute. All right, so that's where we're gonna stop for today. Hopefully you were able to follow along and fill out your notes packet. The next video is going to cover how to open and use Excel, and then we'll have another one that talks about how to open and use RStudio. So thanks for hanging with me, and I'll be back.